September 26, Lecture 1, Atoms in Motion. September 26, Lecture 1, Atoms in Motion. September 26, Lecture 1, Atoms in Motion.
For 2 years, I'm going to lecture you on physics. I'm going to lecture from the point of view that you are all going to be physicists. It's not the case, of course, but that's what every professor in every subject does. So assuming that you're going to be physicists, we're going to have a lot to study. There's 200 years of the most rapidly developing batch of knowledge that there is. So much, in fact, that you might think that you can't learn all of it in 4 years. And you can't. You have to go to graduate school, too. But the surprising thing is that in spite of the tremendous amount of work that's been done for all this time, it is possible to summarize all this to a very large extent. And that is to find some kind of laws which summarizes all our knowledge. Nevertheless, it's still very hard, and it's unfair for you to start exploring this subject without some kind of a map or an outline of the relationship of one part of the subject of science to another. Therefore, the first 3 lectures here will be in the form of outlining the relation of physics to the rest of the sciences and the sciences to each other and the meaning of science. Incidentally, each lecture here will begin by some kind of a description of what the point of the lecture is going to be. Then the lecture proper will start. Previous to that, there'll be a summary of the previous lecture, the bare minimum from the lecture before that is necessary to keep track of. In the first 3 lectures, nothing is necessary to keep track of. None notes need to be taken because what we're trying to develop is a feel for the subject. Of course, you can take down anything that you find interesting that you'd like to remember, but that's about it. After 2 weeks or so, there will be a copy of these notes will be available. Are we going to have some kind of a way of converting these words into print? Now you might ask, why can't we teach physics by just giving the basic laws on page 1 and then just showing how they work in all the various circumstances? Something like Euclidean geometry. Here are the axioms and you make all the deductions. Now you're not satisfied to learn it in 4 years, you want to learn it in 4 minutes. Well, we can't do it that way for 2 reasons. First, we don't know all the basic laws. There's an expanding frontier of ignorance. But we still don't know, though, the answer to everything. Second, the correct statement of the laws of physics requires some very unfamiliar ideas and requires advanced mathematics in their description. Therefore, you need a considerable amount of training first in order to learn out what the words mean. So it is not possible to do it that way. Therefore, we can only do it piece by piece, yet each piece or part of the whole of nature is only some kind of an approximation to the complete truth, or the complete truth as far as we know it. In fact, even everything that we know is only some kind of an approximation, because we know that we don't know the laws yet. Therefore, a great deal must be learned only to be unlearned again, or more accurately, to be corrected. Now, the principle of science, the definition almost, is the following. The test of all knowledge is experiment. Experiment is the sole judge of truth with quotation marks. The quotation marks mean scientific truth, or what we accept to be scientific. Anything is judged always by an experimental test. But what is the source of the knowledge? Where do the laws come from that are going to be tested? Experiment, too, in a sense, produces these laws, in the sense that it gives hints. But you also need imagination to create from these hints the great generalizations, to guess at the wonderful, simple, yet very strange patterns beneath it all. And then to return to experiment to check again whether you got the right guess in your imagination. This imagining process is so difficult that there is today a partial division of labor in physics. There are theoretical physicists who imagine, deduce, and guess at new laws, but don't experiment. And then there are experimenters who experiment, imagine, deduce, and guess. I said that the nature or the laws of nature are approximate, and we first find the wrong ones, and then we find the right ones. How can an experiment be wrong? First, in a trivial way, that something was the matter with the apparatus that you didn't notice, but these things are easily fixed and checked back and forth. So granting that the minor things are taken out, how can the law deduced from experiment be wrong? Only by being inaccurate. For example, the mass of an object never seemed to change. A spinning top, for example, has the same weight as a still one. So a law was invented. Mass is constant, independent of speed. That is now found to be incorrect. The mass does increase with velocity, but appreciable increases require velocities nearly that of light. A true law is, if an object moves less than 100 miles a second, the mass is constant to within 1 part in a million. And see, in some approximate form is correct law. So in practice, you think that the new law made very little difference. Well, yes and no. For ordinary speeds, we can certainly forget it and use a simple constant law as a good approximation. Yet for high speeds, we are wrong, and the higher the speed, the more completely wrong. Finally, in a most interesting way, philosophically, we are completely wrong with the approximate law. Our entire picture of the world has to be altered when the mass is changed only by a little bit, if it isn't constant. That is a very peculiar thing about the philosophy or the basic ideas behind the laws. Very small effects require profound changes in our ideas. Well, what should we teach first if we're going to teach? Should we teach the correct, more exact law with its strange and difficult conceptual ideas? For example, in this particular case, a theory of relativity, four-dimensional space-time, and so on. Or should we first teach the simpler constant mass law, which is only approximate, but does not involve such difficult ideas? The first is more exciting and more wonderful, more fun. But the second is easier to get at first, and is a first step to a real understanding of the first idea. Now, this problem arises again and again in teaching physics. And at different times, we'll have to resolve it in different ways. But in any case, it's worth knowing at each stage what we are learning, how accurate it is, how it fits in to everything else, how it may be changed when we learn more. And therefore, in the first 3 lectures here, we're going to try to give an outline of a general map of our understanding of science today, so that you can, in particular physics, but the other sciences at the periphery, from the point of view that we're taking here. The purpose of these first 3 lectures, then, is to get a feel for the whole thing so that when we do concentrate and look very closely at a particular point, we had some idea of what the background is and why that particular point is interesting and how it fits into the big structure. So that's the purpose of the first 3 lectures. In other words, the first 3 lectures are the main point. What is our overall picture of the world? Now, we're going to begin the first lecture, which is on atoms in motion. If in some cataclysm all of the scientific knowledge is to be destroyed, but only one sentence is to be passed on to the next generations of creatures, what would be the best thing, the thing that contains the most information in the least number of words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you want to call it, that, well, things are made out of atoms, little particles that move around, are in perpetual motion, attract each other when some distance apart, but repel being squeezed into one another. In that one sentence, you'll see there's an enormous amount of information about the world if just a little imagination and thinking is applied. In order to, it's the purpose of this lecture to illustrate that idea, and I do it this way. Suppose that we have a drop of water, say 1/4 of an inch on a side. If we look at it very closely, we see nothing but water, smooth, continuous water. Now, if we magnify it with the best microscope, light microscope, I mean, that's available, roughly 2,000 times, then the water drop would be 30 feet across, about as big as a room or so. And if we look at it closely, we've seen that it is, again, a relatively smooth water, but here and there, a small football-shaped thing swaying back and forth, very interesting. Those are paramecia. And you may stop off at this level and get so curious about the paramecia with their wriggling cilia and twisting bodies that you don't go any further in this particular line, except to hope that you could make the paramecium still larger and see what's inside. This, of course, is a subject of biology, but for the present lecture, I must pass that and go down still further. Man, looking at the raw material itself and magnifying it 2,000 times again. Now the drop of water extends from here to Los Angeles, about 15 miles across. And if you look very closely at it, you'll see a kind of teeming, something that appears, it's no longer smooth. It is something like a crowd would appear at a football game as seen from a very great distance. In order to see what this teeming is about, we'll magnify it another 250 times so that you get a better look at this thing, and we'll see something like what's shown on the first slide. This picture of water, magnified 1 billion times, is idealized in several ways. In the first place, the particles are drawn in a simple manner with sharp edges, which is inaccurate. Secondly, for simplicity, I've sketched it almost schematically in a two-dimensional arrangement, but as you'll most appreciate, these things are moving around in 3 dimensions, and it's very much harder to draw. So this is not a real picture, but a kind of idealization. I would like you to notice that there's 2 kinds of blobs or circles here. Those are the atoms. There's an atom of oxygen, which is made in black, and an atom of hydrogen is pictured as a white circle. And you'll notice that each one has 2 hydrogens tied onto it. There's another way in which this thing is idealized, and that is that the particles in this picture really, in fact, are always in motion. They're in a continuous jiggling and bouncing, turning and twisting around one another. So you have to imagine this in a dynamic way rather than a static way. Another thing that cannot be illustrated in a drawing is the fact that they are stuck together, that they attract each other, that this one is pulled toward this one and by itself, so the whole bunch of them are glued sort of together roughly in a big clump. On the opposite hand, they do not pass through each other. If you try to squeeze 2 of them too close together, they do repel. So we have this picture of jiggling balls bouncing around in the water. As a consequence, the coastline drop of water 15 miles across is now 250 times 15, or from here to Chicago approximately, or bigger. And you can remember the size of these atoms roughly this way. You can either remember that the atoms are from between 1 and 2 times 10 to the minus 8 centimeters in diameter. 10 to the minus 8 centimeters is also called an angstrom. So we say this is another name. So we say there are about 1 or 2 angstroms in diameter. Another way to remember the size is this. If you take an apple and magnify it to the size of the Earth, then the atoms in the apple are approximately the size of an apple. So that's another way. That's either way. You can remember it either way. Now you can imagine in this great drop of water with all these things stuck together and tumbling over each other. The water keeps its volume. It doesn't fall apart because of the attraction of the molecules or the atoms for each other. Supposing if you had a slope, for example, that in the tumbling they can move a whole drop of water from one place to another. The water can flow, but it doesn't just disappear. The things don't just fly apart on account of the attraction. Now the motion is what we represent, or what we notice rather, as heat. And when we increase the temperature, we increase the motion. If we heat the water up, the jiggling increases, the banging between the atoms or molecules increases all the time, until there comes a time when, in a collision, there's so much speed that this pull between them is not enough to hold them together, and they fly apart and become separated from one another. Of course, what I'm describing is the manufacture of steam out of water by increasing the temperature. The things flying apart because of the increased motions. So the next picture, next slide, we had a picture of steam. Now it is much more clear how the molecules are formed. This picture of steam fails in one respect. In ordinary pressures, atmospheric pressure of steam, there might be only a few more, not very many molecules in this whole room. There certainly wouldn't be as many as 3. Most squares of this size would contain nothing. And I accidentally have 2.5 or 3 in the picture, but that's just so it isn't completely boring. You know, 3 things to look at. You see the characteristic molecules are much clearer in the case of steam than they are in the case of water. In this molecule, I've drawn them on the slide, so there's a 120-degree angle here for simplicity. In actual fact, the angle is 105 degrees, 3 minutes. And the distance between the center of the hydrogen and the center of the oxygen is 0.957 angstroms. So we know this molecule very well. In fact, we probably know it better, but I couldn't get more accurate figures in the short time available. Now let's see what some of the properties are of steam vapor or any other gas. Because these things being separated from one another will bounce against the walls. Imagine this room with a number of tennis balls, or not very many, 100 tennis balls or something, bouncing around in all directions because of the heat that they have in perpetual motion. Then they'll, of course, bounce against the walls and bombard it, and this pushes the wall away. Of course, you hold the wall back. That means that the gas exerts a pressure, which, of course, senses, not having ourselves magnified a billion times, we feel it only as an average push. So in order to confound a gas, we have a pressure. So here is a picture, for example, of a standard vessel for holding gases in all textbooks, which consists of a cylinder with a piston head on it. Well, I don't know why oil gases are always contained in cylinders with piston heads, but that's what we will represent here. Now, it doesn't make any difference what the shape of the water molecules are, so for simplicity, I've drawn them as tennis balls or little dots. And these things are in perpetual motion in all directions. So many of them are hitting all the time the top piston, and in order to keep it from being patiently knocked out of the tank, slowly knocked out of the tank by the continuous banging, I have to hold the piston down by a certain force, which I call the pressure. For really the pressure times the area is the force, but never mind. Clearly the force is proportional to the area if, when I increase the area, I keep the number of molecules per cc the same. Now, if I put twice as many molecules in this tank at the same speed that represents them the same temperature, but twice as number of atoms, it's twice the density, then within an excellent approximation, the number of collisions will be twice as much, and they will be as energetic as before, and the pressure will be increased by a factor 2. So the pressure is proportional to the density. Not exactly, because there are forces between these atoms. There's a certain density when they put too many in there that one pulls the other back and decreases the force that you'd expect, perhaps, or increases it because they take up each other's room, and so on. So that it's not so easy to tell exactly, but to an excellent approximation, if the pressure is low enough that there are not many atoms, the force is proportional to the density. Now you can see something else. If I increase the temperature without changing the density of the gas, that means if I increase the speed of the atoms, what's going to happen to the pressure? Well, they hit harder because they're moving faster, so the pressure increases. You see how simple the ideas of atomic theory are. Let me take another example. It's still more. That's another, well, let's consider another thing. Suppose that the piston is moving down while the atoms are being compressed into a smaller space. What happens when an atom hits a moving piston? If it's moving around like this and it hits a moving mirror or bounces off a moving wall, evidently it picks up speed from the collision. You can try it by bouncing a ping-pong ball off a moving bowling ball, for example. And you'll find that it comes off with more speed than it would in. Special example, if it happens to be standing still and the piston hits it, it'll certainly go down. So it's clear that it comes off on average with more speed than it comes in. Therefore, after a while, the atoms which are in here will have picked up speed. That means that when we compress a gas slowly, the temperature of the gas increases. So under slow compression, the gas will increase its temperature. And then the slow expansion will, in the case of expansion, if the piston is moving up, then each atom which hits this piston which is moving out goes in, if I may crudely speak of it, into a yielding material, a place thing that's going back. And the energy that the atoms have is decreased. Therefore, gases cool on expansion. Now that's the direction, an increase in the temperature of the water. Let's look in another direction. Suppose that we decrease the temperature. Suppose that the jiggling of the atoms, of the molecules or the atoms in the water, is slowing down all the time. Now you know that there are forces of attraction between the atoms, and after a while, they can't be able to jiggle so well. What will happen at very low temperatures is indicated in the next slide. What happens is that they lock in to a new pattern. What pattern of, will you turn out the lights so we can see the ice better? To a pattern which is solid. In this particular schematic diagram of ice, which is wrong because it's in 2 dimensions, but is right quantitatively, I have a 3-dimensional model here to I'll explain perhaps later. We have the oxygen atoms and the hydrogens, with 2 hydrogens on each oxygen as before, but they're all, the hydrogens are touching each other and the whole thing is stuck together in a certain array. This is not the exact array. Of course, it's a 2-dimensional thing. The exact array, of course, is a 3-dimensional thing. Let's have the portray. However, the part that's interesting is that the material has a definite place for every atom, and you can easily appreciate that if somehow or other I were to hold all these atoms in a certain arrangement, in a certain place, then because of the structure of interconnections, which is rigid, the other end, miles away, would have a definite location. So if I hold a piece of ice or a needle of ice at one end, the other end resists my pushing it down. Unlike the case of water, in which the structure, because of the increased jiggling, is broken down so that the atoms all move around in arbitrary ways. Then the organization of the atoms in this thing, even if they're held in place, will let pass itself from atom to atom in all directions to the other end. And that little crystal will just sag and drip down as we increase the temperature. So the difference between solids and liquids is that you're solid. The atoms are arranged in some kind of an array, and an array of what's called a crystalline array, a crystalline array, and they do not have a random position at long distances, but the position of some of the atoms at a long distance away is determined by where the atoms are, some millions of miles on the other side of the crystal. Of course, I mean millions of miles at this scale, of course, a small distance in nature. This particular slide is an invented arrangement for ice, and it contains several of the correct features of ice, but is not the true arrangement. One of the correct features is that there's a pattern, a symmetry that's hexagonal. You can see it if you turn this whole picture, I don't mean out the border, but the atoms themselves around an axis, say here, by 120 degrees, for example, then the picture returns to itself, so that there's a symmetry in the ice, a 6-sided symmetry, which accounts for the 6-sided appearance of snowflakes, for example. So in there is the form of snowflakes hidden. Another thing that's illustrated by this particular artificial model is the fact that, particularly, that ice shrinks when it melts. So not this particular pattern that's arranged here had lots of holes in it. Now, the true ice structure has a lot of holes in it. And when the organization breaks down, these holes can be occupied by the molecules. And so the volume of the water is less than that of ice. Most substances, with the exceptions of common substances or exceptions are water and type metal, usually in things contract, expand when they melt, because usually the packing is tighter than this when it's cold, and when it melts it needs more room to jiggle around, so that usually it expands. But sometimes when it's an open structure, it collapses when it melts, as it does in the case of water. Finally, I may say that although this is how I keep talking about this as a rigid arrangement, ice temperature can change. Ice has heat, if you wish, and you can change the amount of heat. What is the heat in the case of ice? Well, these things aren't really just standing still there. They're jiggling in place, vibrating, trying to get out of there, all jiggling, like a wiggling all the time, like a, well, I don't know, you take a mattress springs or something and imagine them all wiggling all the time. So there's a definite order to the thing. It's got a structure, but they're all, the things are jiggling in place. As you increase the temperature, they jiggle in place with a wider and wider shaking until the shaking is so wide, so big, that they pull themselves out of place and we get the melting. As you decrease the temperature, the jiggling decreases and decreases until at the absolute zero, there's a minimum amount of jiggling that matter can have. Not zero, but there's a certain minimum amount of jiggling that matter can have. As a matter of fact, this minimum amount of jiggling that things can have in all cases is not enough to melt the thing, so everything is solid at absolute zero with one exception, and that's helium. Helium never solidifies. The minimal jiggling at absolute zero is still enough to keep it melting. So helium at zero temperature even never freezes unless the pressure is made so high as to help the things that get squashed together. If you increase the pressure, then you can make it solidify. Now that's so much for the description of solids, liquids, and gases from the atomic point of view. But the atomic point of view also describes processes. And so I'd like to go and look at a number of processes to see how they look from an atomic standpoint. The first process that I would like to look at is associated with the surface of the water. What happens at the surface of the water? And this time I'll make the pictures more complicated and realistic by imagining that the surface is in air. And this is illustrated in the next picture. Here is a surface of water in air. You may notice the water molecules as before, and down here and below is the liquid water. And this is the surface solid. Above, you'll find a number of funny things. First of all, there's some water molecules, like the steam. That's water vapor that's always there above water. There's an equilibrium between the vapor, or steam vapor, and the liquid water, which I'll explain in a minute. But in addition, we'll find some other thing. Here's two black ones stuck together. The black ones are called oxygen atoms, and two oxygen atoms stick together also by themselves, probably another kind of molecule or oxygen molecule. In addition, there's these cross-hatched things, which are nitrogen atoms, and they stick together in pairs too to make a molecule. It consists almost entirely, with a few impurities of different things, of nitrogen, oxygen, some water vapor, and a few other things, carbon dioxide, argon, and traces of other things. So here's the air, a gas, containing some water vapor. Now what's happening in this picture? The molecules are not always jiggling around. From time to time in the jiggling, one near the surface happens to be hit a little harder on the accident, just an accident, a little harder than usual, and gets pushed away. Say, I mean, it's hard to say because there's a still picture just what's happening here. But this one has just been hit, for example, and is flying out. Or perhaps this one is the one that's just been hit and flying out. So that molecule by molecule, the water disappears and it evaporates. But if we close the vessel above, after a while we have a large number of molecules of water amongst the air because they have nowhere else to go. In other words, if you ever close the vessel, the water, none of that happens. Then, let me take this one. From time to time, one of them that's out here comes flying down into the water and gets stuck again. So that what looks like a dead, an interesting thing, a glass of water with a cover that's been sitting there for 20 years, is a dynamic, it's an interesting phenomenon going on all the time. To our deaf eyes, our crude eyes, nothing's changing. But if you could see it 1 billion times magnified, you'd see that from its own point of view, it's always changing. Molecules are leaving the surface. Molecules are coming back and forth. Why doesn't it change? Because just as many are leaving as are coming back. So in the long run, nothing happens. If I then take the top of the vessel off, take the glass off, and blow the air away, if I make a stream that sweeps across here and takes away these molecules of water, replacing them just by AM, then the number that are leaving, it's still the same as it was before because it depends on the jiggling of the water. But the number that are coming back is reduced very much because there are so much fewer molecules above the water. Therefore, there's more out than in, and it evaporates. Hence, you want it to evaporate, turn on the fan. Now there's something else. Which molecules leave? When a molecule leaves, it's because of an accidental extra accumulation of a little bit more than ordinary knocking or banging. Therefore, those that leave have on the average more energy than the average molecule that's in here. So the ones that are leaving take away energy and leave the ones behind with a less average motion than they had before. The more moving ones are the ones that leave. So the liquid gradually cools if it evaporates. Of course, when one comes back, because of the attraction to the water below, when it comes in, there's a sudden grow attraction and there's a snapping, in other words, a generation of heat. So when they're coming back, they generate heat. When they leave, they take away heat. And the result, of course, in that when there's no net evaporation is nothing. There's no change in temperature. But if I blow so as to maintain a continuous increase in the number, the more going out than coming in, then the water is cooled. Hence, blow on soup if you want to cool it off. I also want you to notice that the processes are more complicated. Not only does the water go into the air, but you can imagine among the collisions that from time to time, one of these molecules may come in here and get lost in the mist and work its way into the water, so that the air dissolves in the water. Both oxygen, which is not illustrated, and nitrogen molecules will work their way into the water, and the water will contain nitrogen. Of course, if we suddenly take the air away, then these nitrogen molecules will leave more rapidly than they come in, and in doing so will make bubbles. This is very bad for divers, as you well know. When you have a high pressure air which you're breathing, then in the blood more nitrogen is dissolved than ordinarily, because high pressure just means a large density of the nitrogen, so that more of them are going in when it's high. When you decrease the pressure, they try to come out and make bubbles. So that's what happens, and the bubbles are not good for the heart. Now that we turn to another process, on the next slide we see another process from an atomic point of view. A solid dissolving in water. Supposed to be put a crystal of salt in the water, what happens? Salt is a solid, it's a crystal, and so there's an organized array, which is cubic arrangement here, of salt atoms. Here's an illustration in 3 dimensions of the salt. Sodium and chlorine. These are, strictly speaking, not atoms, but what we call ions. An ion is an atom which has either got an extra or has lost a few electrons. It has the wrong number of electrons. And this is a chlorine ion. It's a chlorine atom with an extra electron. And this is a sodium ion, that is to say a sodium atom with 1 electron short. Now they all stick together by electrical attraction in the solid salt. But when you put it in the water, you'll find that because of the attractions of the negative oxygen and positive hydrogens for the ions, there will be gradually in the jiggling, some of these atoms will get loose. Here's a picture of one, the chlorine atom, getting loose. And there they are floating in the water in the form of ions. You'll notice these pictures are made with a great deal of care. You notice some delicate features. For example, around the chlorine, the hydrogen end of the water are more likely to be there, while around the sodium, the oxygen end, because the sodium is positive and the oxygen end of the water molecule is negative, and they electrically attract, so that that's the way it'll be, and it's more or less realistic. And of course, I can't think of everything, so I can only point out those things which are realistic in the slide. Those things which aren't, I haven't thought of. Now, in this particular case, sir, ion by ion, the sodium is this dissolved in the water. Now, how can you tell from this picture whether this is salt dissolving in water or salt crystallized ionized water, say, which is evaporating, an increase in the concentration of salt? You cannot, because for a while the atoms are leaving, other atoms are coming down. We still have this dynamic business, just as we had in the case of evaporation. And it depends upon whether there's more salt in the water or less salt in the water than the amount needed for equilibrium. By equilibrium, I mean the rate at which they're leaving shall match the rate at which they're coming back. So if there's hardly any salt in the water, if it's nearly pure water, more leave than come back and the stuff dissolves. If, on the other hand, you've made it so there's too many atoms or too much in the water, then more come down and the thing is crystallizing. Notice that, by the way, if you're interested in molecules, that the concept of molecules is only approximate and only exists for a certain number of substances. Although it's pretty clear in the case of water that those three atoms are stuck together, it's impossible to say in the case of the sodium chloride, well, the molecule is. There is no molecule of sodium chloride in the solid. There's just an arrangement of sodium and chlorine atoms in a pattern, the cubic pattern given here. If we increase the temperature, we increase the jiggling, then the rate at which the things are taken away is increased. But so is the rate at which the things are brought back increased. And it turns out to be quite difficult in general to predict the general law as to which way it's going to go. When you increase the temperature, whether you're going to dissolve more or dissolve less. Most substances dissolve more, but some substances dissolve less. So we can't tell, but we can guess a little change one way or the other, because it would be an accident of the greatest form if, when you increase the rate of jiggling, the rate at which they jiggle loose and the rate at which they work their way back happen to be balanced, or change both the same amount. Both rates are, of course, increased, but the question is which increases the most. Now, in all the processes which I've described so far, the atoms or the ions have not changed partners. That is, we had here a molecule of water with two oxygens and a hydrogen. We pointed out there was something like oxygen, which was two atoms of oxygen alone. But there are circumstances in which the atoms take up new combinations, forming new molecules. This is illustrated in the next slide, a situation in which the realignment of the partners occurs. This is what we call a chemical reaction. The others we call physical process, but there's no sharp distinction between these three. Nature doesn't care what we call her. She just keeps on doing it whatever way she wants. Now, this is supposed to represent carbon. I didn't bring a crystal of carbon. It's diamond, for example. If you want to burn a diamond in air, you can, but you're kind of dopey. Now, here's burning an oxygen. I simplified, I haven't got air. This is the oxygen. Now, in the case of oxygen, these two oxygen atoms stick together very strongly. Why not three? Why not four stick together? That's one of the very peculiar characteristics of interatomic forces. They're very special, and they like certain particular patterns in certain particular directions and so on. And it's the job of physics to analyze why each one wants what it wants. But at any rate, it forms saturated or happy a pair. The carbon atoms in the crystal, which will be the graphite or diamond, looks like this. Now, for example, one of these can come down to the carbon and each one pick up a carbon atom and go flying off in the new combination, carbon-oxygen, which is called the gas carbon monoxide, one oxygen for each carbon, and is given the chemical name CO. It's very simple. This is practically a picture of that molecule. The carbon attracts the oxygen much more than either the oxygen attracts the oxygen or the carbon attracts the carbon. Therefore, when this happens, this may come down with a small energy, but it may be able to pick up these things, and they will snap together with a tremendous vengeance and jiggle, and anything else near them will pick up the energy away, because if you hit something that's jiggling hard, you pick up an energy. So there's a large amount of motion energy, kinetic energy in the gases generated here. This, of course, is burning. We're getting heat out from the combination of oxygen and carbon. The heat is in the form, ordinarily, of the high motion of the gas, hot gas. But, of course, in certain circumstances, it can be so enormous that it generates light. And so you get flames out of this. In addition, the carbon monoxide is not quite satisfied. It is possible for it to attach another oxygen. So we might have a much more complicated reaction, illustrated here, in which the oxygen is combining with the carbon, but we're not sure, and at the same time there happens to be a collision of a carbon monoxide here, and we're not sure whether this oxygen is going to end up attached to this, on this one to that, or how. But this could attach itself to this and form this molecule, which is one carbon and two oxygens, which is made in the form CO2 and this carbon dioxide. If you've got enough oxygen present and you burn it continuously, you keep the reaction going, it'll form all carbon dioxide ultimately. But if you burn the thing with very little oxygen and do a very rapid reaction, like in a gas, for instance, in an automobile engine, where the explosion is so fast, there isn't time for it to make much, all the carbon dioxide and a considerable amount of carbon monoxide comes out. The main difference between this and other processes is the fact that new particles are formed to form new molecules, and this rearrangement is a clear chemical reaction. And most interesting, in such rearrangements, a very large amount of energy is released, forming explosions and flames and so forth, depending on the reactions. Now, the chemists have studied these arrangements of the atoms and find that everything can be understood. Everything is some kind of an arrangement of atoms. And to illustrate this, I would like to just take an example of something else. If we go in our field and smell violets, for example, what that smell is some kind of a molecular arrangement of atoms that's worked its way into our nose. So, first of all, how did it work its way? Well, it's pretty easy. It's some kind of a molecular arrangement of atoms with the come off of the violet. Since the gas has all the atoms pretty far apart, it can, jiggling around and batting all over, accidentally work its way into the nose. There's no particular desire to get into the nose. It's merely that the jostling crowd of atoms in the air, and this particular chunk of stuff working its way gradually up into, happen to work its way into the nose. Now, the chemists can take special molecules like the odor of violets and analyze it and tell you the exact arrangement in space of the atoms. Just like we know that the carbon dioxide is a straight line from here to here, that can be determined easily by physical methods too. But in the very much more complicated arrangements of atoms that there are in chemistry, by a very remarkable process of detective work, you can find the arrangements of the atoms. First, let me illustrate the picture of how it looks like under a violet, what the air looks like in the neighborhood of a violet. That's illustrated in the next slide. Here is nitrogen and oxygen of the air. What's that? The water vapor. What's it doing while the violet is wet? I mean, you know, all plants transpire, and so there's some water vapor in the air. And then there's this monster. The white circles are carbon atoms, the little circles are hydrogen atoms, and the black circle is an oxygen atom. And these gentlemen have picked a certain particular pattern for them to arrange. It's much more complicated than carbon dioxide. It's an enormously complicated arrangement. Unfortunately, I cannot really picture all that is known about it chemically, because it is actually known in 3 dimensions, the precise arrangement of those atoms. That is, whether, for example, you see I draw it in 2 dimensions, but this carbon and that one may be turned this way relative to this carbon and that one, and so on. And these 6 carbons which form a ring here do not form a flat ring, but a kind of puckered ring. And what are the angles? And distances are known to, say, 1% in this particular case. However, for the excitement of the thing, I unfortunately made this slide almost 9 years ago. And then it turns out that my respect for chemistry was a little bit exaggerated, because they since found that they had made a slight error in the arrangement of the odor of violets. However, I'll tell you what the error is. It's not very great. But I want to point out that what a chemical formula is merely a picture of such a molecule. When the chemist writes this thing on the blackboard, he is trying to draw, roughly speaking, this. He's not drawing it exactly in 3 dimensions, but tells you which atoms are touching which. So I have, for example, a ring of 6 carbons and a chain of carbons hanging out the end. And so you see a ring of 6 carbon and a chain of carbons hanging out the end with an oxygen second from the end, 3 hydrogens tied to that carbon, 2 carbons and 3 hydrogens sticking out the end, so on. So the chemist, in writing this formula, has discovered the arrangement of the atoms in the shape of the molecule. How does he do it? He mixes bottles full of stuff together, and if it turns red, it tells him there's 1 group of 1 carbon, 3 hydrogens tied on here. If it turns blue, on the other hand, that's not the way it is at all. This is one of the most fantastic pieces of detective work that has ever been done, organic chemistry, to discover the arrangement of the atoms in these enormously complicated arrays by looking at what happens when you mix the different substances together. The physicists never quite believed that the chemist knew what he was talking about when he told the arrangement of the atom. And in more or less recent years, in 20 years, 30 years, it's been possible through electron diffraction to kind of look at such molecules. Not quite as complicated as this, but ones which contain parts of this. And it's been possible to locate, sometimes nowadays, yes, even as complicated as this, and it's been possible to locate every atom by a physical method. There's nothing to do with mixing and looking at the colors, but by measuring where they are. And lo and behold, the chemists are almost always correct. Incidentally, I must apologize for this particular one, the order of violets, being unknown. Then it turned out that they had an error in analysis. I picked the wrong molecule. I should have picked one 9 years ago that they knew better. At any rate, the correct picture of the order of violets is given here. It's the same ring as before, same chain as before. If you look closely, you'll see one difference. There's an extra CH3 tied on here. There's a rearrangement of the hydrogens. There's none here, and there's an extra one here, and so on. But it's very close to the way it was before. And I'm sorry I could have made a new slide and not embarrassed the chemist. The substance that I've drawn here is alpha iron, and it turns out that there are, from the violet, 3 different molecules which have a slight difference in the arrangement of the hydrogen atoms. That's all. Minor shifts to a hydrogen atom, to the other form. Now, an important problem in chemistry is to name the substance so you know what it is. Find the name for this shape. And you appreciate the problem of finding a name for a shape, more than a shape even. Not only must you get the shape, but you have to tell which is, this is an oxygen, not a nitrogen. Exactly what they are. You need a name for the shape and the particular location of the atom. And so you can appreciate that the chemical names must be complex if they're complete. And so you see that the name of this thing in a more complete form, that'll tell you the form of it, is 4-Cana-2236-tetramethyl-1-cyclohexanol, close parentheses, -3-butene-2-ome. And that tells you that this is the arrangement. But you can appreciate the difficulties that the chemists have, and also appreciate why the names are so long. It's not because they want to be obstinate, but because they have an extremely difficult problem to describe this thing in words. Why they don't just draw the pictures all the time, I don't know. It seems to me easier. Now, how do we know that there are atoms? By all of the effects that I talked about, with that hypothesis that there are atoms, and one after the other things come out the way we say they ought to if they're made out of atoms, and that's the most of the evidence for atoms. There is somewhat more direct evidence. A good example of that is the following. The atoms are so small that you can't see them with a light microscope, an ordinary microscope. In fact, even today with an electron microscope, you can't still see individual atoms. But with a light microscope, you can see something that's much bigger. Now, if the atoms are always in motion, say in water, and I put a big ball of something in the water, much bigger than the atom, that ball is jigging around, much like a push ball in that big game of a great big ball. A lot of people in there all pushing in various directions, and the ball moves around the field in an irregular fashion. So in an irregular fashion, a very large ball will move because of accidental inequalities of the collisions on one side or the other. A few more hit on one side than the other at a given moment, and the ball starts moving this way. Then it quickly changes its mind and so on. Therefore, by putting in, if you look at very tiny particles of dirt, well, of stuff, of different things, colloids or something in water, through an excellent microscope, you can see a perpetual jiggling of the particles, which is a result of the bombardment of the atoms. That's the most direct evidence for the atom, and I hope that it will be possible to arrange in a laboratory to set up a microscope so that you can take a look at these vibrating atoms. I have here arrangements of the various, some of the different kinds of solids. Here is a solid that's a little more complicated, which is quartzite, and the actual crystal of true quartzite sits here, and you can see the relation between the shape of the crystal and the shape of the arrangement. Here is another arrangement that the chemists are using to study the arrangement of the atoms and various molecules. This is about as complicated as iron. It happens to be an amino acid important in living things called tyrosine, but it's merely illustrative of what we know about the atom. Now, everything is made out of atoms. That's the key hypothesis. The most impressive hypothesis in all biology, for example, the most important hypothesis is that everything animals do, atoms do. In other words, that there's nothing that the living things do that cannot be understood from the point of view that they're made out of atoms jiggling according to the laws of physics. This has not been self-evident from the beginning. It took some experimenting to suggest this hypothesis, and now it is accepted on as the most useful for producing new ideas in the field of biology. If a piece of steel or a piece of salt consisting of atoms one next to the other, can have such interesting properties, or take water, which is nothing but these little blobs, mile upon mile of the same thing repeated on and on, forms waves and foam and makes rushing noises and makes the funny patterns as it runs over cement. If all this, all the life of a stream of water can be nothing but a pile of atoms, how much more is possible if instead of arranging the atoms in some definite pattern, again and again repeated on and on, or even in little lumps of complexity like the ordo virus, we make an arrangement of atoms which is always different from place to place, with different kinds of so on. In other words, enormous arrays, continuously changing, not repeating. How much more marvelous is it possible that these things behave? And is it possible that this thing that's walking back and forth in front of you, talking to you, is a great glob of these things in a very complex arrangement, and that the sheer complexity of it staggers the imagination as to what it can do? So that when we say I am a pile of atoms, I do not say I am merely a pile of atoms, because a pile of atoms which is not repeated from one to the other might well have the possibilities which you see before you. Thank you.